Hello everybody. So we're still talking about the introduction to the Matlab partial differential equation toolbox, and in this video I'm gonna start with the basic mathematical terminology and mathematical symbols that we will see. And as we said in the previous video, the equation that you are gonna pick is gonna be related to the field that you are interested in. So it's gonna be in terms of diffusion, in case of or diffusion coefficient, in terms of temperature, in case of concentration. So this is not the point that I want to raise. The point is the gradient and the divergence. These are the main two terms that I'm interested in because they're going to be there in almost all the equations that we'll see. And to understand the difference between the gradient and the divergence and what is the meaning of these two terms and what is this inverted triangle here, we need to understand the difference between two terms. There is what we call a scalar quantity and a vector quantity. I think many of you would be aware of this, but in case of a vector quantity or a scalar quantity, it's a quantity that is fully defined by just defining its magnitude. So it's, if I say the concentration is 0.5 moles per liter, if I say the mole fraction is whatever, if I say the temperature is 50 degrees Celsius, so this is enough to understand all what you need to know to get a clear idea about the parameter that you're talking about. But in some other cases, the parameter has a magnitude and has a direction. If you say you have a velocity, then you cannot say that velocity is 1 meter per second because you have to know in which direction is this velocity going. If you're talking about flux or a rate, in case of heat transfer or mass transfer, then you must know exactly where is this flux going. Is it going this way? Is it going this way? It's going up or down, whatever. This direction is important. So by just defining the magnitude, you are not fully defining the system or this parameter. So you have to define one other parameter, which is the or know one more information, which is the direction. And the direction is defined based on the reference directions or the reference coordinates. And we have three types of coordinate systems that we deal with. We have the Cartesian coordinates, which define a unit or a point in space by defining the x, y, and z. And this is the simple, most logical or most commonly used method of defining points in space. And in this case, you can say that anything will, or any vector will have a component in x direction, component in y direction, and component in z direction. So this is how we define the direction to get the component of this vector or this quantity in each of one of three main dimensions. In case of the scalar quantity, we can get the derivative of this quantity, but the derivative in 3D space is not gonna be dc. For instance, if it's concentration, you don't say it's dc by dx because there is dc by dy and dc by dz. So to put the three together, you call it the gradient of c, and the gradient is for scalar quantities, and this is or the symbol that's used for it is the inverted delta, which is called nabla, or we call it del. So I say del Ca or nabla Ca is the gradient of Ca, and it's defined as the derivative of C with respect to x in x direction plus the derivative of C with respect to y in y direction plus the derivative of C with respect to z in z direction. So this was originally a scalar quantity, and the C is a scalar quantity, and del C is a vector quantity because it has three components in x, y, and z directions. You can use this for many systems, but there are other systems that are going to be hard to define within or using this coordinate system. So in case you have a cylinder or you have a pipe, a tube, or any cylindrical shaped geometry, then it's easier to use the cylindrical coordinates, where we define a point in space by the r, theta, and z. So let's say this is the center line of the cylinder. So r is the radius, and theta is the angle from this this axis here. So by defining r and theta, you are defining this whole plane. And then by defining z, which is the height, you define this point exactly in space by r, z, and theta. And in this case, the equation is, as you see it here, it's gonna be partial c partial r, and then partial c partial theta, and then partial c partial z. You have here 1 over r. I mean, this is because it's in cylindrical coordinates. The last shape or the last coordinate system is the spherical coordinate system, and in this system you define a point in space by r, theta, and phi. So phi is the angle from the z-axis, theta is the angle from x-axis, and then r. So you can fully define this this point, where r is the distance from the center point of the sphere, and this is the and this is the gradient of c in spherical coordinates, which is this equation. So this is the derivative in 3D for scalar quantities, which is the gradient, and we call it grad c, which is the gradient of c. If you are dealing with a vector quantity, then it's gonna be called divergence. It has the same symbol, but we put dot, so it's del dot n. And this is the derivative of the of a vector in general, and this converts a vector quantity into a scalar quantity. So if you and we call it divergence, so it's div for divergence. In Cartesian coordinates, it's gonna look almost exactly like the case of the gradient, but in this case it's scalar, so I don't have ex, ey, ez, so it's just scalar quantity. The divergence of n in case of cylindrical coordinates will take this shape. It's kind of more complex than the the gradient, and here is the shape of the equation in case of spherical coordinates. So this is I think there is a mistake here. This is just one partial r. I think this is a mistake, so I think I'll delete this. So this is the equation. So for the next part, or this is important because we need to understand the way we put the inputs to MATLAB. And here it's important to note that this software is gonna be depending on your basic knowledge of the field that you are you're solving. So if it's mass transfer, then you have to have a good understanding of the mass transfer equations. If it's heat transfer, then you have to have good knowledge of the equations that you have, and to understand how to translate the equations that you know into the inputs that the software requires from you. So for instance, here I'm showing you the window of inputs or the partial differential equation specifications for the diffusion. So in this case, this is the equation that you have. So you have types of partial differential equation. There is the elliptical and parabolic. So these are two shapes. For each one of them, the software shows you the equation that you are solving, and this is why I have been talking about the gradient and the divergence, because you will not be able to understand this equation unless you understand the difference between them and what do they mean. So this is the exact same equation here. One thing here is kind of confusing, is that some symbols are not put with the same symbol that we are, or some parameters are defined by symbols that are different from the symbols that we are used to. So for instance, in this shape for the elliptical equation, it says negative divergence of d multiplied by gradient of c equals q, which can be mathematically represented as we see here. It's negative del of d del c equals q, which is the steady state continuity equation. This is the steady state continuity equation. But this equation, the shape that we're used to is like this. This is the left hand side, but the right hand side is the rate of reaction, or the rate of production. So it says here the volume source, which we are used to as the rate of production. So it's the same. So if you want to put it like this, then it's gonna be okay. But just to understand that this corresponds to this, the RA corresponds to Q. There is another form of the equation which is almost the same, but with the C dash, which is the steady state, the unsteady state case. So here you have the C dash, which is the change of C with respect to time. So this is the second form of the equation. And here you would notice that you define the diffusion coefficient here. And by defining the diffusion coefficient, it's defined once. The software assumes that the diffusion coefficient is constant. So it's gonna be defined once, and you're not defining it more like later, even in the boundary conditions. It's already defined here. So these are the two shapes of the equation that you deal with. And then for the boundary conditions, there is a similar window, and the boundary condition gives you two shapes of the boundary condition with the equation here. So this is the equation that we have. It says n multiplied by d multiplied by gradient of c plus q multiplied by c equals g, which is this. So the g is the flux. So this is n. There are sometimes boundary conditions that is n equals something. So this is n, and q is the transfer coefficient, which is heat transfer coefficient in case you have heat transfer coefficient or the boundary condition as convection. So this is the shape of the equation, and this is d multiplied by gradient of c is the diffusivity multiplied by the gradient of c, might be a shape of a boundary condition. I don't know what this n is, because it doesn't give you an option to put the value of n, but anyways, I don't know. I just assume it's 1 for now, until I know later. And maybe if I can know, I will let you know when we go to this point. The last boundary condition here is the, I think, I don't know if I'm pronouncing it right, but it's called Dirichlet or Dirichlet. I think it's something like this. And it says h multiplied by c equals r, and it took me some time to understand what does it mean, but after some trials and some experiments, I was able to figure out that this is giving you concentration as r divided by h. It says here r is concentration and h is weight. So it's like putting c as a constant. So I don't know why we didn't just put c equals r without h, but anyways, this is how it's defined. So in case you have boundary condition of concentration equals to 10, you will put r equals 10 and h equals 0 equals 1, and that's it. So this is how you define it. So this is all for now. In the next video, we will start, inshallah, we will start talking about the software in more details and see the steps of the solution. So I'll see you then, inshallah. Goodbye.